Welcome to the session. Greeting of the day. In today's class we are going to talk about the process controllers. In the previous classes we have seen about the various PID controllers and various other digital controllers we have seen, such as microprocessors, microcontrollers, PLCs. Those things we have defined. We know that. And one more process of the process controllers are there that we have to see. The characteristics of P, I and D. This is what we have seen. The proportional controller Kp, the constant we have done, will have the effect of reducing the rising time and it will reduce, but never eliminate the steady state error. This steady state error only we have seen now. It never reduce the steady state error. So that is what we have understood. This steady state errors keep on coming there. So what we can do now? I am adding an integral controller here. In an integral controller, the manipulation equals the integral of the error over time and multiplied with the constant of Ki. K is integral or integral time. How long it takes, now I am understanding. Proportionally speed is given 10 meter per second, 50 meter per second we have given, but it is not reaching there. It is showing some steady state error. I am integrating the same one with respect to time differences and I am doing. So this point we should understand here. You see, we have given on point that here that it works on based upon the present error. The P is going to work upon the present error. This present error is a steady state error. It is happening now. Now it is happening. I know this is going to happen by the previous experiments. I am controlling, giving the input of with respect to the past error. I know if we are going in the 5 meter per second, we won't reach. If I know the past error comes at less than that, I know if we are moving in 7 meter per second, we won't reach. This is the past error, we know. And I am planning now for 10 meter per second and we will reach. So here we have done with the 5 meter per second, error came. That is present now, not happening. We know we should not go in 2 meter per second, we should not go in 7 meter per second, we know. With respect to these causes, I am doing some integral operations to move by with respect to 10 meter per second. Then with less time, I will reach there by the graph. So that is what. So that is what we understand with respect to these causes. You see, here we have done these things. Input given, so the comparator, and here I have taken 1 by TIS, that is nothing but a integral time, how fast we should do this. So I am taking. Now the time reduction will happen with the comparison of the past errors. We can able to do quickly and we can avoid this long time taking process. I have taken 2 meters per second unknowingly. Just we can move for 2 meters per second, we will reach 50 meters. It takes more time. Okay. Now we will go for in the 55 meters per second, it will take more time. So these are the past errors I am considering and I am planning to move by 10 meters per second. So that is what I have planned in such a way. This is a constant indicating that is integral. Integral only. What I have to do? Here additionally I have to do proportional. P and I, two connections are there. So likewise, what happens? 50 meters to be reached by the drone. Errors are there, steady state error are there. So it is not possible. Therefore, I have added the integral part. I have added the integral part. Along with this gain factor of 5 5, 3 we have tried. This interval part, we have the present data, this is, we have given some point 2, 1, 2, we are trying. And this past information also we have taken into account. And now it is going to work. And we will reach the same, and the 0 meters we will reach, error is 0, but it is running at 100 RPM and it is constantly moving. So we are getting this feedback. Yeah. So this is one part. Now you see, in this integral part, what happens? This error, steady state error is not there. Steady state error is we have reduced from with respect to giving the past memory information. I have read steady state error has been avoided, but we have not possible to avoid this overshooting and undershooting process. What is this overshooting and undershooting process? We have done here. 100 RPM is maintained and we have cancelled the steady state error and we came. But it is not possible to maintain this overshootings and undershooting process. You see, it follows like this format of graph it is going to follow. Here we have this over and undershooting process are happening. So what we have to do now for this graph? We have to add these derivative processes. We have to add these derivative processes in such a way it can able to avoid. See this graph? Here we have done the integral. It is quickly done. We have reached there, but the shooting is over. Overshooting is happening. This overshooting is happening. Overshooting is happening. So we have to derive this. Slowly, when we are reaching at this point itself, we should derive in such a way that you should not go there. What happens then if you are going into 10 meters per second? 10 meters per second, when we are reaching there, our speed is to be reduced to 2 meters per second. And automatically we will be on the track. If the same speed is maintained, we will go upward, then we understand we have reached the level and slowly we will reduce. So that should not happen. We should go steadily, reach and then move. Therefore, I am adding the derivative part here. How I am adding? See, this is what the graph it will look. It increased taking diversions. It is increasing and it is taking the diversion part. See? So this is overshooting. So this is what the overshooting, and this underlying part is the undershooting. So likewise, if this all should not happen. Now what I am doing, this is what will happen. We will have the effect on this two we have completed. Proportional controller will have the reducing of rising time. Slowly it will rise. You have planned to rise quickly. But what happens? It should not have the shooting times. That I am planning. But never eliminate the steady state error. So this steady state error are avoided here. The steady state errors are avoided. We will have the effect of eliminating the steady state error. Here it is eliminated. For a constant, we reached the level. But what happens? Reaching level is not important to be maintained, but it is not maintained. It is going up and down, the speed. But it make a transient response slower. So up and down, overshooting. Undershooting. This is happening. I am coming to the derivative part. Derivative control uses the derivative of the error instead of the integral. So I am giving the constant name as TDS, derivative time. So I am adding this now. How it will look? So by the present, I have planned 2 meters per second. By the past, we should not move by the memory. we should not go on 5 meter per second. Therefore, I have went on 10 meter per second and we have reached the level. We have reached the level. But what happens? The shorting happens. I want to reduce now. So derivative, the future not to be like this. Therefore, when I am going here itself, this 10 meter per second converted to 5 meter, then 2 meter, and slowly it reaches there and can't make it as constant. So that is a part done by the derivative. First input is given. First 5 not going. So it is converting this integral. Then it is stopping those integral value to slowly to not to overshoot. So these things I am doing here. So what happens? This rate of change to be reduced. We are first going at this rate. When it is reached slowly, when it is coming near a rate of distance to be reduced slowly. Error quickly to reduce. What is error? When you are going upward is error. Coming downward is also error. So error to be reduced when we are coming nearby. This is the point where it should come nearby and it should reduce. So that is how I can able to understand. Look at a current rate of change of error. At the current rate, how fast we are moving, then we can able to reach that line. So immediately it will respond back, reduce the speed, walking speed or motor speed or automobile speed, whichever it is, we convert and we are making the steady line. Determine how we are approaching the goal and permanently slow down the propellers of this for this exam. So this I think is visible here. See, it has went here. Immediately it is getting steady state. No such responses like this. No such responses like this are not there. It takes time. This is red color is belong to PID. This blue color belong to integral. And then one more line we can draw. Slowly it increases. This belong to proportional. I need this PID. I not need this proportional. We are reaching here, but slowly we are reaching, and we don't know where at what time we will reach 2 meters per second. And we have given the input of 10 meters per second, but what happens? It is overshooting is happening here. This overshooting is happening. This is also not to be happen. Therefore, I am derivating and giving the rate of speed slowly while before it is reaching there. I am reducing this integral part and converting. So it may be the graph can be formed in this way. Along with it will go. Slowly it will and it reaches the line. The track of 50 meters. So likewise we can able to do. So this is the what I have drawn there. So finally we understand the proportional will have the effect of reducing the rising time at the same time, but will never eliminate this steady state error. This is what happened. This I am reducing here. Eliminate the steady state error for a constant set inputs. Now, but what is the other problem here? But we make a transition response slower. Very slowly it is going to make like this. So now I want to reduce this also. I am using the derivative. We will have the effect of increasing the stability, reducing the overshooting, improve the transition response quickly. So this is the advantage we are getting. So I want to use in a combined way. I need speed. I don't need a steady state error. I don't need of overshooting. We reach quickly, softly, steadily. I am comparing this now. You see, I have to compare. Problems and advantages I have taken. Proportional controller, it has the problem of steady state error, but it have the advantage of speed control. 2, 5, 10 we are giving input here. Proportional along with integral I have added. Now integral I have added. Now it means the slow response and overshooting. That is a problem. Overshooting not to be takes place. This overshooting, this is the shooting. This is overshooting. This is undershooting. Not to be happen. And what is the advantage here? This steady state is advantage here. It is not happened here. Steady state is not happened. We are reaching PID controllers. So it is not a problem. So this is separate. This is advantages. Completely advantages. Decrease the rise time. Rise time slowly it is not rising. Decreasing the rise time. This is the rise time. X and Y. This is the rise time. Instead of going that point, we are reaching here itself. Decreasing the rise time. It decreases the maximum peak. It means shooting. Decreases the maximum peak. Decreases the overshooting. Decreases the settling time. What is the settling time? You see, settling time. It may go slowly and come here. It may come here. It may come here. Shooting, undershooting, shooting, undershooting, shooting, undershooting, shooting, undershooting. Slowly it tries to control itself and reaches. This is settling time, and we are reaching this constant value of 50 meters at a long time here. Not to happen. This settling time to be quick. When we are adding the derivative control, it comes here slowly and it can. Because overshootings are avoided, undershootings are avoided, steady state errors are avoided, and we are planning to the state fixed parameter through PID controllers. So that decreasing the settling time. So this is what we have to see. A change in one of those variables can change the effect of 2. With the PID controllers, we can able to set a P, I and D values so that we will not have the over or undershooting or reach the set point quickly, directly. PID controllers have all the necessary dynamics, fast reaction on the change, increasing the control signals to the lead errors, and suitable actions inside the controller area to eliminate the oscillations. So this all are advantages of this present, past and future trends we are using for this PID controllers. Have variety of applications are here. Variety of applications. What are they? You see, PID controllers are having use in the water level management, oil level management, head positioning of the disk drives, automated inspection and quality controls, CNC mechanisms, chemical processing plants, automatic control of material handling systems, automatic packaging and dispatching. So the various applications are there for this PID control, because we need process, monitoring, continuous monitoring, steady state error to reduce, constant value to be there, error to be 0. Then we use this PID controllers. Right? The summary. In today's class, we have seen about the process controllers. On this process controllers, we have started to see about the proportional controllers, the integral controllers, and then the derivative controllers. And we have understood these three and we have combined to form a PID controller for the usage of error 0, constant output. Okay. The remaining part of the subjects we will see you in the next session. Thank you.